Good. So, yeah. Camera rolling. How well did everybody sleep? Better than the nights before or not? Is it? In my case, yes, but not quite enough to boost me to regular energy levels. But let's see how far we get today. That is also one of the biggest reasons why we're now talking about graph summarization rather than, well, on the topic of IIDness, how can we do with models. I frankly didn't have the energy to prepare a complete new lecture this week. I mean, I apologize dearly, but right, I mean, that's blame the weather gods or whatever it is. So this would have been the lecture that in a different, in a parallel universe, I would have lectured before last week's lecture. So I'm now flipping the order a bit around. We already discussed a few of the things from this lecture last week, right, at very like hand-wavy aspects. So we'll see in how much depth we need to go. But there's still a number of things here that I think are very much worth discussing. And well, there's multiple sides to this lecture. So I also want to use it, given that this is the penultimate lecture of TADA, right? I mean, it's one of my favorite words, penultimate. You don't get to use it so often, but it sounds so eloquent. So I want us to exercise a little bit what we've learned in the last few months on the topic of critical thought and creative thought and so on and so forth, right? And that, so I would like to discuss with you the topic of graph summarization. The question of the week, of today, is how can we summarize the main structure of a graph in easily understandable terms? And with main structure, I mean, well, what is truly of interest, right? I mean, rather than just some very plain statistic. So normally I would start by going to the second slide and then doing blah, blah, blah. But let me start with, and I know this is a big ask because everybody is still a bit sleepy. Any ideas? What could we do? I give you one giant graph. And I mean, I presume that everybody knows what a graph is. Otherwise, I will need the next few slides, but then just raise your hand. How can we get the main structure of a graph? And why is this harder, easier, or same as for, let's say, a table or what we saw earlier in sequences? What could we do? Just fire whatever stupid idea you have. We'll work from there. Magnus.
Can, for example, try to decompose the graph?
How would we do that? How do we decompose a graph?
Like, for example, decomposing it in nodes that are highly connected and other groups that are not that connected.
Yeah.
Thanks.
Okay. Yeah, that we could do. I mean, that we'll touch upon this topic at one moment during the lecture. What does this give us? So this is something we can do. I mean, there I agree, right? I mean that, and I also agree that this is something somewhat meaningful towards the goal of summarizing the main structure. But what do you have in mind? I mean, so it's more like the why rather than the how.
Gives us at least some ideas of the component of the graph. Yeah, I mean, I still don't know what main structure actually means. So
me neither. I mean, what does main structure mean? I mean that. So one thing that we could do is we could, well, count the average degree. So we count the number of edges, right? And we divide it by the number of nodes. Does that tell us something? I mean, something, yes, obviously, right? I mean, it's if I just draw a random number, that would be no, but.
Take over the entire graph, but there might be some local structures that you can miss by just doing some kind of summary.
Yes, yes. So it would give us something, but also not. Okay, good. I will revisit this question a number of times during the lecture, or so I plan at least. And then we'll see if we have gained some new thoughts or not, right? Or if you do, I mean, raise your hand and interrupt, right? I mean, that today is the lecture for that. So first of all, no lecture on graphs is complete by pointing out that graphs are everywhere and that essentially any data type and data structure can be modeled as a graph. Almost everything, that is. Sequences, like we were discussing 2 lectures ago, obviously, right? And well, even a table, I mean, if you make the nodes, I mean, there could be attributes with values, and then you just have entities connecting to them. We'll see a few examples in a minute. Formally, we have G is a tuple of vertices and edges, right? Both sets, n nodes, m edges typically. We can make this as fancy as we like. We can give these nodes labels, we can give the edges labels, we can give them weights, we can make them directed, we can give them a time span over which they live. We can put functions over the and so on and so forth, right? We can also consider hypergraphs, where you have edges between sets of nodes, right? Both left and right, rather than just pairwise. For example, if A and B are really connected to C together, then you have a different type of edge. We're not going to be looking into that today. We boil it down to the simplest case of undirected, unlabeled, unweighted, etc., graphs, right? Effectively those where we can represent the entire graph by just looking at the adjacency matrix, just a binary matrix, and where we only have to look at the upper diagonal. Because the lower diagonal, I mean, if it's undirected, then it's just going to be a copy, right? So that saves a lot of work. Now, I do this on purpose because right now it's really didactic reasons. We can make things more fancy, but why would you if we're not yet there? It is also what happens in most, not all, but most work on graphs that you'll find in the literature. And almost everybody will write, I mean, it is easy, it is trivial to extend this to directed graphs, so looking at both sides, and weighted and so on and so forth. Take this trivial always with a rather large grain of salt. Sometimes it is, sometimes it isn't. And it is almost always left as future work, and including the ones that are non-trivial. But if people then do try to solve it, reviewers put up a huge roadblock because, yeah, well, it has already been done for undirected blah, blah, blah graphs, right? So it is typically hard to, if you don't do it in one go, like tackle a more real graph, methods often stay stuck in, well, not so real graph land, making the applicability a bit limited. Just some examples. I mean, networks are obviously graphs, right? I mean, that's so we have 4 of them from different domains. I mean, no big surprise there. The one I personally like best when we're talking about graphs are relational databases. And this is not because I love databases so much, but the called relational database model is just simply super powerful. And you can, in a very compact way, in a queryable, sounding complete way, store your information. And effectively, this is also a graph. It is not a graph of the kind that we'll be studying, right? But in theory, what we have here, we can extend to also relational databases. On that note, if we have this picture or this slide here up, if we now look a bit into the now, lots of things are using graph neural networks or GNN based, right? I mean, that, which is basically, well, it's agglomeration, accumulation of it's basically message passing in the end. I mean that so you average information at multiple distances, you accumulate this, and then you make a decision. So it is graph based, but it's not as graphy as people often make you want to believe, right? Even though it's called a graph neural network. Now, standard GNNs are terrific for the 4 on the outer sides. You can use them in theory for relational databases, but they typically start to break down because, well, this simple type of averaging agglomeration does not really work so well. Which makes that a very interesting topic to study because there is a metric shit ton of information stored in relational databases. I mean, every self-respecting company will store stuff in a relational database and not just have it on one big heap or some kind, right? And information is simply connected. So there is a huge, well, research hole right in the middle here, just from the GNN perspective. Okay, now I also need to do the obligatory. The internet is also, of course, a graph, right? And that means both, well, how things are connected on the internet as well as everything that goes over the internet. So do we need graph methods? Sure. Already said, unlabeled, unweighted, undirected graphs, adjacency metrics. For a node I, we can identify the degree, the number of edges that it has, as d of I. Yeah? Because we were talking already earlier about, okay, well, perhaps we can then compute an average over those, right? That might hide some local structure, but hey, globally it might make sense. Okay, the story in my head is a bit different than on the slide. So why do we want to summarize at all? Real graphs tend to be big. They tend to have millions, hundreds, thousands, millions of nodes. So hence these averages also start to become more and more meaningless because there are just going to be many, many subpopulations. Also towards visualization, standard visualization techniques, and these are already the advanced ones, basically don't tell you so much, right? And that's, so tables, we can, well, you can have like pairwise correlations, I mean triple correlations, you can plot things. Sequences, we also have all sorts of, let's say, frequencies that you can, in graphs this becomes very difficult and you end up with, well, what we call then a hairball. This would be roughly a hairball. Here's already identified that there are some bipartite graphs. So we want to understand the graph. Just staring at an adjacency matrix is kind of useless. What do we see here? Does anybody see any structure? Exactly. There's a, yeah. That is what you can tell, but the rest, would we say that, wow, look, in the top left, these bands, they are really more densely connected than this part here in the middle? Would anybody say so, or would you be careful to say so? You should be careful. Because if I permute this matrix, I can make it look like essentially anything, right? I mean, this is almost random. There is some basic structure, but not much, not much. So staring at an adjacency matrix does not really make so much sense. This is an edit graph of Wikipedia. So there is some structure, but no. So this is now a true hairball, actually not even there because even here we impose some structure. What do you do with this, right? I mean, these are Wikipedia edit graphs where for specific articles, we show if people have been editing these articles, right? And there is, so we call this the controversy. This has been before the Ukraine war, but there was already an edit war going on Wikipedia between Russian-speaking and Ukrainian-speaking people on how to write Kiev, amongst others. There were a few other topics. And well, you sort of did these edit wars. And of course, this sort of creates two camps, right? I mean, this is camp one, this is the other camp. These are nodes that are basically users that edit a remarkable large number of articles, make a remarkable many edits. That could be bots, could be, well, overzealous, overpaid bots, but then in human form. There we are. So that was one of the reasons why we would like to be able to pick out this is a structure and whatnot, right? But I mean, so what can we do? Average degree. We also said so. I mean, this is not very insightful in that sense. We can perhaps plot the degree distribution, right? Because that would also tell us, I mean, if every node has roughly the same degree, then hey, then the average is meaningful. And if not, okay, so let's plot what degrees, right? So how many nodes of what degree do we have? You've seen the slide, then with the big fat power laws on top of it. This is the main result of the Falutzos cubed paper, where for a whole bunch of real world graphs, they did exactly this exercise that I just said. So this is then the in degree, and this is the number of nodes, pages. These are internet web pages. I think this is for a router network, I mean, also an in degree, and this is the number. And what they found, if you take a log of this, a log plot, it's remarkably linear. And you find this in almost any real world graph. Now, what does log and then linear mean? That means power law. What does that mean? That means an exponential distribution. And what does an exponential distribution not have? What is the key property of the exponential distribution? It does not have an average. Because the exponentiality, there's always going to be this one user with an insane number of followers. But there's going to be an insane number of people with almost no followers, but very low in degree. There is no average. It just has a shape and, well, a certain curve. That's the summary statistic there. But average is meaningless. So same thing on Facebook. The vast majority of people has almost no friends on Facebook or on Twitter and so on and so forth. And well, a few will skew the distribution very heavily in the other direction. You could say, okay, well, we can always compute the median, right? Median is a bit more meaningful, except that for these power laws, well, that will drag it very much to this vast majority of people who almost have no in or out degree. So it's again kind of meaningless. So whenever you think of average, you also have to think, okay, what is possibly the distribution, and does this distribution even have a meaningful average? Good. Well, something that is slightly more useful is the so-called cluster coefficient. And we can compute this at different levels. So let's first stick at the global level, just like an average, right? But in a way, what we're now computing is a meaningful average, if you wish. We try to answer by a single number, how clustered are the nodes in the graph? So effectively, what we're interested, what do we mean by clustered? Is that we have 3 nodes. Are they fully connected? Do they form a triangle, right? And of course, we could compute this for every triplet of nodes. Well, that is a bit stupid, right? I mean, that's unless we really know that the degree, that's basically the matrix is full of ones, right? I mean, that, so rather what we want to do, we take 3 nodes that are connected, that share this at least 2 edges, right? So we can fold them into, well, at least a line. And then we check, are the endpoints also connected? So for every line, is it a triangle? Bit of a weird thing to say, but you probably know what I mean, right? And that we count. Now, okay, counting triangles, actually, and just for the intuition, right? I mean, if the graph is a full clique, then every triplet of nodes, I mean, has at least this line is also so, right? I mean, that if the entire graph is just a line, well, we have many of these, and all of a sudden it will be 0, right? Okay, this gives you a bit of the intuition of this measure. Now, in Graphland, one of the key things that you always have to keep in mind is, can you even compute this? Is this scalable? How would you do this? Here, I mean, this is a quite innocuous approach, right? I mean, we just have to count triangles, but how difficult is this now exactly? You need matrix multiplication. So, okay, n to the power omega, and omega, this is basically ongoing work in theoretical computer science. How can we most efficiently multiply 2 matrices? And current, you call it, coefficient is, well, 2.376. Perhaps we can do a little bit better, but chances that we get it at or below 2 are 0, because that has also been bounded. So that means we are super quadratic. Now, if you have your average table or an average, well, let's say, size data set, I mean, quadratic is not even so bad. Although we were the other day interested in some challenge where the data available is 300 million well, genetic sequences. Okay, if you have 300 million, then quadratic is also all of a sudden a bit sketchy, right? I mean, but in a graph, most definitely, because if we now want to compute this for, let's say, the Facebook graph, I don't know the actual user numbers of Facebook, but a few billion, apparently. A billion squared, that's a large number, right? I mean, that's where even Meta starts to scratch their heads. Okay, do we want to compute this exactly? Or maybe not, right? So, okay, yeah. Fast estimators exist. I'm not even sure if these give guarantees, but that's a bit besides the point. But just to highlight that even something as simple as this metric is already almost incalculable in practice on a real world graph. Okay. Let's go to the local variant, because the global one smears it out over the entire graph, which would mean that if I have half my graph is a clique, right, and the other half is a chain, right, I mean, the value that I get would slump completely, right? I mean, that would get a weird average. That doesn't tell me anything. So basically, it would just say that my graph is half connected, which is true, but also not really. So we can also compute this score per node. So how clickish is the neighborhood of a specific node? Effectively, what we do, we take a node, we take every pair of adjacent nodes, and we see, and adjacent means that they have an edge, right, from I to J, I to K, right? And then we check, are those two also connected? Which again, if I lives in a click, then we end in one end of the spectrum, and if it lives on a line, right, or a star, actually, I mean, that's the generalization of a line, then, well, we get a very low cluster coefficient. Now, this we can compute a bit, well, easier. So it's squared in di, but that is just for one node. So, and if you have this one node that is connecting, so in a power law, it could be that there's this one node that connects to every other node, you're again screwed, just for calculating this one stupid value, right? I mean, that just to get a glimpse of, like, even boiling it down does not make things easy necessarily in graphs. So, and you also need squared space. So, yeah, not so great. Good. Of course, here also fast estimators exist. I mean, you can build a randomized algorithm, right? I mean, where you just sample from adjacent nodes and see, and then, well, if you do this in a smart way and you're gamble on being lucky, then you get very quick, good estimate. I mean, that randomized algorithms are your friend in graphland often. Okay. What actually is a useful global summary statistic of a graph is that of the diameter. And the diameter is the longest, shortest path between any two nodes. Or between any two nodes, what is then the longest? So which two nodes are furthest away from each other? This gives a bit of the connectivity structure of the graph. And for example, if a graph is a line, we get a very high number, right? And if it's a click, well, then it's a very low number, right? So it gives us something what is in between. Now, what is interesting about the diameter, because the proposal is of course very simple, but in real world graphs, we now have already seen we have these power law distributions. Another way of phrasing this is that it's called the small worlds phenomenon. And this goes hand in hand, right? I mean, the small world phenomenon was already known, the power laws, not necessarily. And that, so people knew that, I'm going to explain this in a second what small worlds are, but they were still modeling graphs very happily as Erdős-Rényi graphs, where basically every node has the same expected degree, which, well, that does not follow a power law. So you can build all sorts of theory and methods that work very well and test them on Erdős-Rényi graphs. But if you then run this method on a graph that actually has a power law distribution, that's a bit like, well, I don't know. If you was apples and oranges, we're thinking of like making a juicer specific for apples, but probably still that works for oranges, but you catch my drift, right? But okay. Now, what is the small worlds phenomenon? Is that in a real world, I would say graph, let's say a social network, this is where it was found, people are remarkably closely connected. I discussed this in passing last week, right? In that, so at the top of my head, it was B.F. Skinner, but otherwise some other famous psychologist, empirical psychologist in roughly the 50s, did an experiment where they sent well, they randomly chose in the phone book some names, and the goal was to get an envelope to, well, the designated person, right? So, and with this goal, they handed out, I don't know how many, but let's say 1,000 envelopes, I mean, addressed just to a name somewhere in the US. Gave this out one by one to people who, well, I'm not certain if in the original experiment, these were randomly chosen or already selected, like, well, you might know that person. But the instructions were, hand this envelope or send it, right? I mean, that's to somebody who you think can get it quickest to that person who you don't even know, right? I mean, that's and if you live, let's say, well, in Saarbrücken, and you need to send it to somewhere to somebody in Berlin that you don't know, okay, maybe you have a friend in Berlin, or maybe you have a friend in Potsdam, right? I mean, you send it to Potsdam, and then, well, maybe they send it to somebody else, whatnot. That's the general idea. From that experiment, of course, I mean, tons of these envelopes went lost, right? I mean, that's like, okay, what the fuck? But actually a remarkable amount, perhaps because people in the 50s were more diligent, I don't know, or maybe the postal system worked better. They actually did forward it, and with a quite large confidence interval, it was somewhere between 5 to 7 hops that it needed on average to reach its destination, which of course is kind of surprising, right? I mean, that why would it take so few? Effectively, what the small worlds phenomenon says is that there are social, let's say, circles, but primarily there are what we now call, let's say from COVID, super spreaders, people who are connected to many, many people. And they might not know exactly, but they can sort of route information very quickly. These are the, well, on Twitter, I mean, these are the Elon Musks, the Donald Trumps, the Obamas, and so on and so forth, right? I mean, that who have a huge spread of information. And, well, you and I, probably a very small one. But because everybody has their own network, and these typically, well, only partially overlap. It's another property of this power law distribution, because the moment they start to more overlap, it becomes more of this heterogeneous graph, which we know it isn't. Therewith, you have very quickly a very high spread over the entire graph. Also, real-world graphs therewith tend to be connected. So there's almost always a path from A to B. And hence, the diameter of a real-world graph is typically very short, much shorter than you would expect just based on average degree. So how do we calculate this? Well, okay, simple, right? We take every pair of nodes and we calculate the shortest path. I see Timur shaking his head. I mean, why not, right? Yeah. Yeah, exactly. And it should have animated in. Exactly. Yeah. So so you can do this in an n cubed algorithm, but yeah, if squared was already scary, then what are we doing, right? And if you implement it really smartly, then you can do n times m. So n is good, right? There's number of nodes. M is number of edges. This is already very scary, right? Plus then n squared log n. So yes, it is faster, right? And it will save Meta a ton of money if they actually use the first algorithm, but this is something you don't want to calculate in practice. Again, randomized algorithms are your friend. And well, okay, this is actually where we already were. Quick aside, but focusing on the, well, n cubed is no, right? I mean, n squared is already no in many cases. I mean, that, if you want to have a method, you want to have it linear or almost linear. We saw this last week too. What are the implications of this? That there is this very big focus, out of necessity, you might say, on, well, having a fast algorithm. Yeah. Mm-hmm. Yes. Yeah. So that is one way to phrase it. But I'm going to ask the question, see if there's more ideas, because I don't want to put words in your mouth. So the underlying question is if reviewers, right, the community, basically only accepts your idea if it's linear. What does that mean for, well, science, knowledge? Goes hand in hand with what you were saying. Timmy? Yes. But that's what it means. But effectively, what happens? What could possibly go wrong? Or the other way around, what does not happen? Magnus?
Maybe you like discard very good ideas, which on first sight are not that scalable, but on second thought you might be able to somehow estimate them or make them quicker. Place, and you just reject the ideas.
Mm-hmm. Yeah. So perhaps, well, it's also related to graphs, but I mean that, but not, let's say, for most people in the first glance. But can you think of an idea that, I mean, is now very popular, but for a long time was basically put aside because of, well, reasons such as those? Neural networks, yes. Yeah, neural networks were stupid. And well, they're still as neurotic as hell, right? I mean, I'm still not a big fan for those reasons, but computing a neural network, I mean, making it pass through, I mean, until GPUs, this was kind of a no-no, right? I mean, that it's really this massive parallel computation. I mean, it is still a beast of a task, but we can now do it more efficiently, right? Similarly, one of the other hiccups was, okay, we needed an insane amount of data, which wasn't available yet, but those are two hurdles that we passed through and we see the advantages. Now, but the main point I wanted to illustrate here is that if you are given these constraints, this is on the one hand fine, because yeah, if we now propose a cubed algorithm, but if the cubed algorithm gives now really the answer that people are truly after, and that gets rejected, whereas the linear algorithm, which doesn't even attempt, well, it can just be computed fast and it kind of looks shiny, but it's possibly going in completely wrong direction. Is this now a good answer, really? I have my doubts there. But I would say that it's always good to think of like what is the real question? What would be the best answer or the best possible answer we can currently come up with for that question? And then start to think, okay, can we make this faster? Basically, which corners can we cut? But by starting from not necessarily the ideal, but let's say the ideal solution and then boiling it down to something that we can actually compute, I'm personally a bit more confident that we have something that we want rather than, well, this is what we can do quickly. Is this the right thing? Well, it works in practice. It's not really my type of research. But yeah, good. Okay, so summarizing a graph. This was our attempt at summarizing a graph in a slightly different way where we get a bit more insight. Now, this connects the non-IIDness topic, right, that we were discussing. I mean, right now it's a bit more focused on graphs. I mean, this last part of TADA. It connects also the patterns back in. Now, if we have unlabeled, unweighted, undirected graphs, the notion of a pattern, as we've seen it before, right, something that happens a lot, what would that be? And is that useful? So let's first look into the question of like, okay, something that happens frequently. I mean, what would it be here in a graph? Jimmy? The degree of the node, yeah, but that would be sort of like so would you say that the degree of, is that really a pattern? That is true. That is true. But so in these tables, right, we had like, okay, well, A and B are often sold together, right? In sequences, we had B happens often after A, something like this. So this is more type of thinking that I'm trying to go towards. Can we do anything with an undirected, unweighted, unlabeled graph? So they're unweighted, unlabeled. But sure, if we make them labeled, right? I mean, there's one thing that we could do. But there's a reason why I have the unlabeled variant here. Well, they're also undirected. But indeed, if they would be directed, and especially directed and labeled, things become easier. So one thing you could do is just count how often do you see certain, what they call motifs, connectivity structures. So let's take triangles, right? If we can easily describe our entire graph with triangles, okay, triangle is a building block. We could do that. Is that a good idea? Is that a useful idea? Magnus?
It depends on what actually a good idea. I don't think it's a good idea because you need a vocabulary of participants. How do you define this? Especially for if you just have a single graph.
Yeah. Well, that is so the vocabulary is exactly where we're going. But let's stick with the triangles, right? What we effectively could do is we can take effectively any subgraph that we find in our actual graph, right? And then count how often do we see them. And then use a similar idea as we had for the tables and the sequences, right? So perhaps it's like a triangle with some thingy sticking out, right? And that actually we see a lot. If we use that as a primitive, then we can describe the connectivity structure of the graph very efficiently. We could define something like this, right? Which might give some information, except that, well, what does a triangle with some tail now really mean, right? I mean, another problem that bites us in the back, especially for undirected, unweighted, etc., graphs, subgraph isomorphism. So we can either put it like this, or like this, or like this, and to find a cover of your graph with the substrate, good luck, right? Now, like I already said, I'm fine with sort of finding first the ideal question to answer and then coming up with an efficient one, but subgraph isomorphism is one of the things that make me say, okay, well, maybe we should be careful before we really venture in this direction. So, but this is this type of finding frequent subgraphs that people studied quite a bit, especially for labeled graphs. So if we give all these nodes a label A, B, C, D, right, then all of a sudden it becomes very close to what we saw 2 weeks ago, or at the beginning of the lecture series. And we can find, okay, a node of type A is often connected to a B and a C, and that you can use. But that was so close to what is already done, right? I mean, on the technical side, it was not so interesting. Plus B, how often do you have graphs that look like this? I mean, if this is, let's say, a friendship graph, then, well, how many Magnuses are, it's one, right? I mean, unless you have a number of ghost accounts, right? But then that's, so then all of a sudden the labels would be okay. Then you need to label people, okay, which are the students or some property, and yeah, it becomes a bit weird. Again, in molecules, there, the nodes have natural labels, right? Carbon, oxygen, and so on and so forth. So yes, for molecules, this has been studied quite a bit. Now, one other thing that we could do is we can define a vocabulary of meaningful graph structures beforehand. So there you could ask, okay, well, perhaps we want to have something a bit more free form, but if I don't know what a triangle with a squiggly is, if this is now real structure or just happenstance, now, if somebody can point out to me that here, these nodes actually form something that is almost a clique, well, then I can put a name onto some nodes. And if we can build up, like this clique is connected through this star, through that biclique, then all of a sudden I get an abstraction that gives me some information what are really the building blocks of this graph. So this is a different type of summarization as we've been doing before. But using these types of primitives allows us to say something a bit more meaningful about the data. No. We could do that in theory, but it is a bit meaningless in a way. So yeah, it's a summary statistic, like, okay, well, how many cliques are there in a graph? Sure, but I rather want to describe these nodes form a clique, these form a that, these have some undefined connectivity structure. So roughly something like this, right? So here we have a clique, here's a star, here's a star, here's a biclique, here's some near clique. And we allow possibly these structures to overlap in the sense that a node may be part of multiple C structures. In this part of the lecture, we do not allow yet that they share really edges, but that's a more technical limitation of the method I'll be presenting in a second. So effectively what we go is that after finding structures, we can remove all the edges that are left unexplained by the structures we found. And this is sort of like the core structure of the graph. That's the idea. So that's what is important. Okay. Now, I need to make a small aside before we can actually start to do this. Because, well, actually, I should first ask, I mean, does this seem like a reasonable approach? You may say no. I mean, we did it, we published it, so that's... I could also say it's one of my most cited papers, but that doesn't make it the best paper by a long shot, right? But finding what is the core structure, I think, is a sensible goal. Timur, yes. Yeah. Effectively, yes. So in let's say the big book of graph theory, we looked up what are now key structure types. We'll see the exact list in a second. But for example, a full clique, but you can also have a near clique. You can have an exact bipartite. You can have a near bipartite clique. There's a chain. There's a star. I think this is more or less it. I think there were 6 components. But you could go for, let's say, stars of stars, these jellyfishes type of structures. Basically anything that we, as in science and graph theory, have given a name to, we could theoretically plug in, as long as we know how to find them in a graph, right? If I give you a graph, it's okay, I have no idea if there's a star here, then yeah, well, what should I do, right? But yeah, so it's a very different approach than with crimp and squeeze and whatnot, where we had a very loose pattern language, and basically, well, you could say it was fully non-parametric. Here, this is a bit more parametric because we give you the vocabulary that you're allowed to describe the graph with.
Find the shape that would describe the graph. Is it just the time boundary?
No, it's more the interpretability. It's the interpretability, and it's the, so in a undirected, unweighted, unlabeled graph, finding these types of things is relatively straightforward and relatively meaningful. If I can split your graph, decompose, and okay, this is a clique and these are just a bunch of stars, that is already quite a lot of information. Whereas the, let's say, a repeating connectivity structure in particularly a social network, I have seen very few, I'm not going to say none, but very few examples that make sense. Let me give an example of why not, right? I mean, that let's look at a Facebook or a LinkedIn. I mean, that LinkedIn was a perfect example there. Some colleagues of mine, they actually looked into this data. What you will find is that triangles are by far the most frequent structure. So effectively, if we would do this loose finding of structure, you will find triangles and essentially nothing else. Why? What could possibly be a reason why we just find triangles? I presume that some of you at least have a social media account, right? And that you typically get these suggestions of contacts, of friends or whatnot, right? I mean, how do you think that most of these algorithms work? Yeah. So basically, these 2 people are friends, right? I mean, so it's basically connecting a line and seeing, is it a triangle? So the algorithm is actively trying to create triangles. And perhaps you know these people, but perhaps also just by the birds of a feather flock together type of effect. Okay, well, hey, he or she is doing something interesting. If we're talking about LinkedIn, click, right? I mean, that's so let's say the graph generating algorithm, if we allow ourselves to think of that, it steers towards finding or creating triangles and not necessarily other things. So the triangles drown out any other type of structure. You can also ask yourself the question, on such a social network, do we really expect complicated patterns? Like, okay, people with a black shirt who share or are in a class with somebody wearing a pink shirt happen to have 5 friends wearing blue shirts, something like this, right? If I focus on shirt, I mean, and that happens a lot in the data. It could be, but how likely is this?
That's defining like another type of node instead. So you take a triangle that you find, or this is another node.
Yep. Yep. So this, I think the method, so it's not exactly doing what you're saying, but I mean, it comes very, yeah. So there's a method called, I think, grasp. I think it's called grasp. I mean, that's, forgot the Lefebvre. I think forgot her first name, something like Catherine Lefebvre and Effie Maria Terzi. They published an algorithm a good number of years ago that gives what you call a hierarchical summary. I mean, that's what they do. They don't really focus on triangles so much, right? But I mean, the idea remains the same. You find some structure that you like. In their case, this was, I mean, some strongly connected set of nodes, right? I mean, that's some more cliques, but bear with me. And you collapse them into, well, a hypernode. And this hypernode now inherits all the connections to other nodes outside of the hypernode that the nodes within what is now the hypernode also had, right? And then we just repeat this until, well, some criterion says, okay, stop, don't do this anymore. Sure, you can do this. You can also do this with triangles. But the key question is and remains, what do we gain? What is now the piece of information we're communicating to the end user? So to a certain extent, so I agree with you, it would be nice to have this more loose structure, but what does it mean? Is it still interpretable? What can you do with it? And on the other side, what would we expect in real world data? I've never found really good answers to these questions. Maybe they exist. Maybe we should just do it. But this brings me to, besides the what can possibly go wrong, to my other favorite type of question. I mean, let's focus on the why before focusing on the how. Because the moment that we say, let's do these triangles, right, these structures, we can come up with an algorithm. I'm 100% certain, right? And maybe we can even make it efficient. And if we do our homework well, we get some patterns, we get some compression, whatever, maybe we can do some classification, we'll get something. But the why should we engage in this? That I would first need to be convinced of before I really invest my time. But I don't want to discourage you at all. And I'm not saying that I'm right and you're wrong, not at all. Florian. Yeah.
Why?
These are structures that we can give a name to. So if you have any other structure that you can come up with that you can give a name to, the Florian graph structure, I don't know what it looks like, right? But we can also plug this in. The vocabulary in this method is very extendable.
Are they
No, no, no. So but perhaps I should first explain the method before when we go too much about what does something you guys, well, I know, but you guys don't know, what does it do or doesn't do, because that becomes a very weird lecture, even weirder than it already is. Magnus.
Like for example, what you do with molecules, you actually have your data set of molecules and then you just mine these structures.
Yeah.
But this of course only makes sense if you have these kinds of data sets, and then you get quite nice motives.
Yes, exactly. Yeah. But this again goes hand in hand. Do you have an attributed graph or not? Right? Because also an example I just gave to Timo, where we said, okay, we have shirt colors. That's already, you have attributes, you have labels, right? So you can really pin specific subparts of the graph and then start to count. And what we also saw 2 weeks ago, that just counting in a sequence quickly becomes difficult. How do you avoid double counting and whatnot, right? With an unweighted, unlabeled, undirected graph, this is a very nasty problem. That the more information you have, the more you can condition, the easier things get. But you do face still graph isomorphism typically.
Really dependent on the vocabulary that they
choose. Yes.
So wouldn't it be better if because for example, if we chose a vocabulary that doesn't exist inside our graph, we would just say that the graph is perhaps by that logic not
exactly. Yeah.
But we let our for example, algorithm like DFS guide our search and then find structures that exist. Wouldn't that be a better something?
Possibly, but the core problem is let me see. So it's really being able to name something. So for example, if we go back to subgroup discovery, right? I mean, why is subgroup discovery, well, qualitatively different, and I would say more useful in practice often than clustering, is that because these points, these samples belong together because A is red and B is above 5, right? These points, and then I see something that is special, right? So it's really, you give a name to the object rather than saying, well, these points are similar, right? I mean, which is a bit more. Now, this is in that line of thinking, we also have this here. So the moment I give you a specific vocabulary, I typically call this then a pattern language, right? That allows you to make certain statements and others not. Of course, that is the lens through which you're looking at your data. But we've always been doing this, right? It's just right now it stares you a bit more into the face, and I'm happy that you guys are so critical, because you should be. I've been doing my job apparently, or the assignments have, or I don't know, something else. For example, if we go back to crimp and slim, we have conjunctive patterns, A and B and C, right? Where we do not allow overlap. It's a very restricted pattern language, right? By already allowing overlap between ABC and CDE, you get very different answers for the same data set. Possibly better, unless your algorithm is screwed up, of course. Same thing here. If I only allow you to describe a graph using clicks, then, well, the star shapes, you're not going to be able to explain. Like, okay, there's nothing to see here, right? And vice versa. If I only allow you to explain it using star shapes, then you will miss the clicks completely. So in that line, you want to have an as extensive vocabulary as possible. But you still would like to be able to say, like, okay, well, these nodes share some structure. That is one statement, right? That is a bit like the type of patterns we've been looking into previously. And here it's more like these nodes share that structure. This structure has a name. This is a bicyclic. And a bicyclic means we have these nodes, they are connected in that way to that set of nodes. And in theory, we could try to discover these types of primitives from data. But this is also very tricky because, for example, we have now, here we have one click, or one near click actually, in the top left. How would we decide, okay, to give this a specific name? It's more clicks or more a structure for graphs in general, right? So in a way, what we're using here with these primitives, this vocabulary, these are names that hold over graphs in general, rather than necessarily for this graph that we see it many times. So it's a different type of pattern language. Here we're describing not so much in frequent patterns within a graph, but more, well, frequent patterns over graphs, or at least structures we are aware that could exist. I'm not saying the one is better than the other, but I wouldn't know yet. And if I would, then we'd be very happy to write a paper about this, how to discover these types of structures. Okay, good. So now, we are not the first to look into graph summarization, but there is an enormous body of work on, typically people call this community detection. And you were very critical about what I just presented. I'm happy for that. And I would love to hear your thoughts about these hundreds of papers where basically people assume that a graph consists of clicks. And that's that. That's the entire vocabulary. And you were saying we can decompose a graph. Effectively, what people have been looking into, how can we break a graph into core components that are strongly connected? So dense subgraph discovery, community detection, there's a number of names for this. And really there's hundreds, if not thousands, if not millions of papers on this. Now, here we have an example that would make most of these algorithms extremely happy. We call this a dumbbell graph, right? I mean, from the gym. And if you then draw the adjacency matrix, it looks like that. If I would give you a graph like this, right? I mean, you should be able to find these two components, right? Now, it's always nice to live in a fantasy world and to develop algorithms for graphs that look like this. But do graphs look like this? Graphs are power law distributed. This is Erdos-Renyi. Do power law graphs have clicks? They can, but do they have these clicks that are really like there's nothing here and nothing, none of these people know any of these people, or vice versa, right? What we started to call these graphs and these communities, when we started this work, are so-called cavemen. Cave women are also invited, of course. I mean, cavemen in communities, because these people, they all live in one cave, and there is one brave person who then perhaps has contact with the other cave, but otherwise the graph is disconnected. This is not how the world works, right? I mean, all of you have friendship circles from elementary school, maybe from kindergarten, maybe you moved a few times, right? I mean, so from other social circles, maybe you do sports, you're at university, and so on and so forth, right? So that a graph can be split like this, very unlikely. Very unlikely. Real graphs look much more like this. And on the right-hand side, we then ordered actually this is the AS Oregon before ordering. We can order this even better. But that's what the adjacency metric looks like. This is not a graph that is very suited for this caveman community detection. Also, one main thing, if we have a power law distributed graph, there are going to be these stars, right? So it breaks it really just in essence. Now, again, short aside, if you have a binary matrix, So it may be a graph. Doesn't have to be, right? It could also just be attributes, so binary attributes, these would be columns. And then we have, in the rows, we have samples, right? I mean, it's a very generic algorithm. This is an old method, it's more than 20 years old by now, but I'd still like to present it because this is one of those algorithms that few people know of, at least people who did not take TADA. And I think it really should be part of the standard bag of tricks. We already saw that many datasets can be trivially reduced to something binary and still maintain most of its information. With this algorithm, you can very quickly see if there are, well, components in this database that are worth investigating. It's very simple. We start with a grid that we impose. Then, given that this is binary, right, for each of these cells, we can compute an entropy. So what is the probability of a 0? What's the probability of the 1, right? And then you know how to compute entropy, I suppose. And what we can now do is iteratively reassign rows, and the next iteration columns, and then rows again, and so on and so forth, such that we minimize the entropy. So that means, for example, right here, is that this row, you see that there's relatively many black dots, right? If I move it into this here, and those ones that, well, have no black here, move it into there, we create a component that is much more pure, you could say, right, on those columns. But you still have these over here, which if we flop those into there, in the next iteration, and so on and so forth, you arrive at a nice checkerboard pattern. This is on synthetic data, right? I mean, this is on what I call a Mondrian data set, right, by the painter Mondrian. Okay, it's not in full color, but I mean, forgive me for that. This is an example of a nice randomized algorithm that even if the data is not as perfectly structured like this, it can tell you very quickly which sets of features, which sets of samples are related or show very similar structure. Okay, now how does it work in practice? We start with original metrics. We randomly create a split. So that is what we have here. Then we do this reassignment. So that would mean that we arrive at this completely. We add another random split. We reassign, then we arrive here, and we keep on doing this until, well, adding a new split does not improve the entropy overall. That final result might be slightly overfit, but I mean that you could refine the MDL score that they're using. Super simple, works well in practice. You can apply this on graphs, attributed graphs, right? But of course, if you have to apply this directly on an adjacency matrix, it's a bit weird that you, well, by moving a row, you're also moving a column effectively, right? And well, that you would have to adapt the algorithm slightly. But even there, it would make sense to find this type of cliquish or off-diagonal clique structure, if you believe in the caveman structures. If you want to go beyond caveman communities, there was an algorithm by I still mean, so I always need to explain the story. So Yu Kang is from Korea, and his first name is literally just the letter U. You can imagine that for you, that is sometimes difficult, right? How often he has, like, if he needs to enter his first name into some form, right? I mean, that says, no, your name is too short. Anyway, super nice guy. Used to be a PhD student at CMU when I was visiting. By now, he's a professor in Korea back home. What we're having here on the right-hand side is the same adjacency metrics that we saw earlier, but after reordering. And I will show you how we've reordered it. But you can all of a sudden see that, well, there is this clique of people who are, well, like densely connected with each other, but with everybody, right? So in a way, these are not so interesting. These are all these star nodes, right? But then on this diagonal, we have a number of cliques. They may seem small, but this has been a very large graph overall, right? So we also see that there is an enormous, vast area where there's essentially no connection whatsoever, right? The original goal of Yukang and Christos Faloutsos here was actually to store adjacency matrices, store graphs more efficiently in a way that you can very quickly query them, right? I mean, that they have roots in database land. And of course, if you now impose a grid over this adjacency matrix, then many of these cells would just be empty. So you don't need to waste any bits on storing it. That was the general idea here. And they came up with the algorithm I'll show you in the next slide to find these types of like these sparse regions to save storage. But when they then had it, like, okay, wait a second. Now we have a fantastic graph decomposition algorithm, which is how we will use it. The method is called slash and burn, and it's super simple. So look at the largest connected component. We do this then iteratively, we can split. Within that, find the node with the highest degree, the most connected node, right? In this case, we call this the hub in that. And we remove all those edges. That is effectively what we do iteratively. So find the largest connected component. The GCC is the giant connected component. This is often what you have. And then find the highest connected node in that, break it, and essentially see if that splits the graph already into islands, and then keep on doing that. And that is the order that you also see here, right? This is why those nodes with the highest degree are top left, and then very quickly, well, so many edges are gone, right? Okay. So hub, split, and now we do the same thing on the GCC. I think this is the simplest algorithm that I have in any lecture, but it's again one of those super useful ones. Not just because you get the adjacency matrix as we see here, and all of a sudden we can see some structure. All of a sudden on here, we can also decide, does it make sense to try to find these caveman-like communities, right? Which are these diagonal blocks. But we also can use it if at any other algorithm, we need to find, well, subgraphs that are potentially of interest. Because effectively, by iteratively removing a node, which is then kind of by definition a star node, right? Very connected to many, and those many may or may not be connected to each other. True star is not connected to each other. But we break the graph into more and more pieces, each of which we can consider in turn as a new subgraph. So super efficient. That's what the idea that we will be using in a second. So now, this is me a good number of years ago. Danai Kutra was working as a PhD student with Christos. She had, well, yeah, basically just started her PhD. She was just done with her coursework. So effectively in UDS terms, she was in grad school, just finished about the prep phase and was now starting as a real PhD student. And she was working on the problem of graph similarity. So given two graphs, how similar are these graphs? They came up with a method that made sense. However, reviewers didn't quite like it. Because, well, how does this measure now compare to my favorite graph similarity measure? You focus on, yeah, let's say they counted the number of cliques in a graph, right? I mean, and they're like, oh, why don't you also count that or such or so? Time and again, they got comments like, yep, I don't want to build an airplane. I want a car, right? And this is a car. Car is fine, right? We can drive over roads. Why don't you go to space? Stuff like this. So she was a bit down and out. But there was also some other reasons, but let's not dive into those right now. I was visiting CMU at the time for a few months. And I was chatting with Danai, like, okay, well, this is nice, but why and how, right? I mean, why is your similarity measure now the similarity measure? What is similarity, right? I mean, similarity is just like beauty, it's in the eye of the beholder, right? I was thinking, okay, can we somehow pin it down a bit more formally that basically people can't really argue with it, right? This is or the notion of similarity. Well, as you by now know, I mean, I like information theory, I like MDL, I like Kolmogorov complexity. Can we use Kolmogorov complexity to define a similarity measure? How would we do so? I mean, just in very broad strokes. Timur. Yeah, but I'll give you two graphs. And I want You to tell me how similar are these graphs. Would that work? So what could possibly go wrong? You're on the right track, but not quite there. Because if I have two graphs that have the same Kolmogorov complexity, but are otherwise completely different, right? Yeah, something like this. So, okay, right? Can we salvage your idea? Look, look. That's my hint. Or second hint for the same thing. Magnus.
The lowest complexity we can compute it if the both graphs are the same, because then we only need one program. If they're completely different, we need two programs.
Yes.
So yeah, we need to encode the similarity between them, save information or
Exactly, yeah. Yeah. So that's indeed the intuition. So if they're exactly the same, we need only one program. Otherwise, we really need two. Now, we could try to find what is now really the same and then encode this separately, right? I mean, so basically in three parts. We'll see this later in the lecture, I mean, time permitting. But what we can do is take your two ideas together. I can, in theory, build an algorithm that compresses them together, right? And see how many bits this takes. And let's say that k bits, right, I mean, is for what we need for one graph, right? I mean, if I now also need k bits for the two graphs, right, this is a good signal, right? I mean, if I need 2k bits, not a good signal. But what is k? Well, for that, we can pick up your idea by just compressing the one graph, compressing the other graph. And effectively, we can define a score, which is the number of bits we need to compress both graphs together, normalized by if we compress them separately. That's what's called the similarity metric. Paper by Paul Vitani was one of the leading experts on Kolmogorov complexity from, I think, 2003, 2005, something like this. I forgot. Doesn't really matter. But you can show all sorts of beautiful properties on that metric. And in a way, it's ultimate. Okay, cool, right? So this is where Denai and I also then arrived. Okay, we would like to have this, right? I mean, how could we build this for a graph? Well, effectively, we can't compute Kolmogorov complexity. But we can replace the k with an L, and then we're at MDL land, right? So all we need is an MDL score and an algorithm to optimize it. How to compress two graphs? Well, that is still quite a big challenge, right? Especially for somebody who's the beginner of a PhD, has never done anything with MDL, right? I was only there for a small amount of time. So then we said, you know what? Let's start simple, because what we need in this formula, at the denominator, we need to encode these graphs separately. So let's start first with a graph compressor for an individual graph. And then later, we will figure out how to do two graphs at the same time, because, well, how difficult can that be, right? That was the general goal. So with the goal of graph similarity, right, to basically salvage or save partially her PhD topic, we started on graph summarization. Her PhD thesis, which won some big awards, was on graph summarization. So I'm not certain if well, she's thankful for me sending her in that direction or now being stuck in it in a way, but no. She's now a professor at University of Michigan and very successful. Good. But Vogue was the starting point of that journey. I'm using, for a large part, again, the same slides from way back then, right? I mean, and I will walk you quickly through it. So the idea you already know. We're going to use a graph vocabulary, basically structures that we can name. We have these five, right? So star structure, chain, clique, near clique, and a bipartite core. But you can also have a near, so where some edges are missing. We're going to be using MDL to find the best summary, which is no surprise, A, because this is TADA, and B, because you know where we actually wanted to go with this paper, but the reader didn't know, of course. I don't need to explain what MDL is. General idea, we have an adjacency matrix that under some ideal permutation looks like this, right? So it's easy to see that there's a clique. It's easy to see that there is a small near clique that, well, overlaps on the nodes. This is a chain. A chain is an off-diagonal diagonal, and this is a bipartite core. Or this is a star, sorry, this is a star. That's the true adjacency matrix, and we model this in sort of this clean version over here, and all the rest of the edges we can't explain, we call them error. This is how we decompose things. And effectively, the more error edges we can explain easily with the vocabulary we have, the happier we are because the fewer the bits we need, right? That's what we try to do. So how does Vogue work? This is the overview. We have our graph. We use some black box algorithm, let's call it slash and burn, to split it into subgraphs. Then for each of these subgraphs, we ask the question, what are you? And we have yet another algorithm to see, okay, well, if you are a star, which is the hub node? Then which are the spokes and what is the connectivity structure? So how many errors are there, right? A true star in graph theory is, okay, you have a hub connected to nodes, but the spokes are not connected, right? I mean, that would be an error. So we need to penalize that. Same thing for a chain, that we want to have a longest path without any shortcuts and so on and so forth, right? So for each of those, we can see how many errors do you make. We can encode this using MDL, and then we see, okay, which one is now most costly, respectively cheapest. In this case, we can say that the graph we're looking at is a bipartite core. Done. Okay, so we give it a name. We do this for all, and okay, the animation is a little bit. And then using some criterion, we select which ones are best, right? That together make the summary. So effectively, these are the candidates, right? The analog of the candidates that we have in CRIMP, and then we have CRIMP selects then these things. It doesn't go really completely hand in hand, but fine. Okay, so that would be the summary, for example. Okay, now let's go now from the start, but slightly less bird's eye view. I mean, so we decompose. In theory, we can use any decomposition method that includes all these community detection algorithms. You can use spectral methods, graph cut, whatnot, right? I mean, in the end, the only thing we want is a subgraph that we then later can give a name to. We don't care. I mean, in theory, you could enumerate every possible subgraph if you have infinite time. Let's not do that. Slash burn, what we do, you already know how slash burn works. We take the hub, we remove it. And what we now do is that we consider the one that we just burned down as a candidate, as well as all the connecting or the structures that we now split off from the graph. Those become candidate structures. And I believe we also take the giant connected component as a sort of mega candidate, but this is a bit immaterial. I mean, the main idea is we split the graph into pieces and we give them names. Structures can overlap. I mean, we stress this so much because in these caveman community detection algorithms, they can't. You're either part of this group or of that group and nothing else. You could fairly say that, hey, but wait a second, if now, let's say there's also some trail here, right? I mean, then if I actually draw this entire line, if I just say this is the entire chain, it also makes sense. Then you would need overlap in edges. That we don't allow yet in this algorithm. Too bad, something's got to give. Okay, how do we label things? We have an MDL cost, sure. This is already said. If we say for a particular subgraph, so here we basically play pretend this is a star structure. How do we most efficiently encode this? Well, we need to find that node with the highest degree. That's going to be the hub. That's the definition of a star structure. It would be a bit weird to say, okay, well, we take a node within this network that has a lower degree than the highest degree, because that would incur also the highest number of errors to the star that we would be otherwise forming. So, okay. So finding a hub, finding a highest degree node is relatively straightforward. For the bipartite core, we need to split the graph into two parts, such that they are strongly connected on the one side and not connected on the other, but are connected in between. For a chain, as we call it, a line, we need to find the best ordering of the nodes, such that we have the fewest shortcuts. So it's basically a depth first search type of algorithm. And finally, for a click, the errors, the notions are basically how many edges are missing. So if I already gave you the graph, that is relatively straightforward because, well, which edges are missing, done, right? So note that max click is NP hard, can't do it. But the moment I give you a graph determining that it's a click, that is straightforward, right? Okay. Now let's give a bit of intuition on how we build the scores for these things. So we have on the Truth Social, right? I mean, this is taken from, I guess, a certain hub node or a candidate. The idea of how to encode this example here, where, well, there are 7 nodes, you can count them if you wish. And as you can see, well, it's almost but not quite a star structure, right? This edge is missing, and well, then those are connected and they shouldn't be, right? If we say that this is the hub. So somehow that's something that we need to encode in the errors. But before we can go there, we first need to identify, well, that it's a star. In an MDL score, you always need to think about what is the core information you need to transmit. Well, for a star, this is initially the hub, right? Okay, if I tell you the hub, then automatically the rest are the spokes, right? Okay, yeah, number of spokes. Right? What is the, how would we encode the, yeah, so the number of spokes is basically the size of the subgraph. I mean, I'll give you this one for free. This is encoding for integers. Well, if I give you the number of spokes, and you know that we're talking about the star, you know that there's also a hub node, right? So that means that I'm implicitly sending 7, but I'm only sending 6. And the idea is that this ln uses fewer bits the smaller the number. So in that way, I shaved off some bits, right? But this, basically, we just send the size of the subgraph. Now we send the ID of the hub node. So we know that there's 7 nodes, right? I mean, but somewhere in the giant graph. So log n. You have no idea which is the hub node. Okay, so how do we now transmit which are the 6 spokes? Well, we have n-1 nodes that can be a spoke because the nth node we already took out, right? So it's n-1, choose, in this case, 6. So, and st is the size of the star, right? Whoops, that's here. And then we encode using a very similar idea which edges are missing, respectively extra. And we do this separately because then we can also weigh these separately if we feel so inclined. Okay. But I just wanted to walk you through this, not because this is the best encoding per se, maybe it is, maybe it isn't, I don't know, I don't care, but to give you the intuition. In a big graph, if you want to tell me, here lives a star, okay, well, you somehow need to tell me this is the hub, these are the spokes, and therewith also the number of spokes and everything. So break it down into pieces, and then you can reason, is this, well, efficient? Are we wasting stuff? Yes or no? Okay, next, bipartite graphs. Max bipartite graph, just like max clique, it's effectively the same subproblem, you can reduce it, is NP-hard. And here we don't, even within like a sub graph, right? I mean, that, so we have a bit more of a problem than previously. So what we can do is we can use some belief propagation, message passing, right? You could now call it a graph neural network if, for all I care. And effectively let these nodes talk to each other and determine which color they like being. And they like being a color if all their friends or many of their friends are of a specific color. And therewith you can find, okay, well, these are the blue nodes, these are the red nodes. Well, you just have to carefully calibrate the message passing such that you get the structure that you want. Now, this is something where Danai had been working on message passing for a long while, so she came up with a very nice heuristic. How do we transmit that there lives a bipartite core in our graph? We don't know anything, right? So first thing that we need to know, how many, which are the nodes? Well, first, then how many of those nodes? How many blue ones, how many red ones? So we have over here, okay, don't even animate it. That's over here. And then their ideas. So same as previously, right? Number of total nodes, choose number of blue. And from the remainder, choose the red ones. And actually, you can do this in a multinomial, you can do it in one go. Doesn't really matter. The errors in this particular case are in case there's any edges missing between the core part, or if there's superfluous edges that are missing between the two cores. Okay. Next up, a line or chain. Longest path is NP-hard in the graph. So this is the one thing that I learned in this project, that everything, well, I have always said that anything worth doing on data is NP-hard, and therewith we need to come up with smart heuristics. In Graphland, it is truly the case. It's like even the simplest things are NP-hard. So how do you find a chain? Well, we can do either depth first search or breadth first search. And basically, you don't want to get distracted by shortcuts. That is the tricky part. So that's the heuristic. How do we encode this? Effectively, I need to tell you, well, if I break it down, how long is the chain going to be? And then one by one, send you the IDs of the nodes, starting with a cost of log n, then a cost of log n minus 1, n minus 2, and so on and so forth. There we are. Okay, and the errors, I need to tell if there's any shortcuts, because in a true chain, there's no shortcuts. As an aside, a few years after this paper, I was working with a student, Patrick Verba, who afterwards did his PhD at the University of Basel, is now done. And we were looking into, well, slimifying this algorithm, because this algorithm is a bit more built on top of, let's say, sort of a crimp type of, let's first find the structures, put them together, right? But a first attempt, we first needed to solve it in a way that we know that what we're after. And one of the things that we struggled with is that because we had some very nice algorithm also for this, but in none of the data sets that we ran it on, we actually found any chains. And that surprised us very much. Because if you think of it, what is a chain? Well, these are a set of nodes that this one is only connected to that one, only to that one, only to that one, right? So real graphs have very large sparse regions. So you would expect a lot of chains. Right? Well, the problem is, and this is, I mean, how do you say voortschrijdend inzicht? I mean, that you gain more and more insight as you go. When we were writing this paper, and I was working with with the world's top graph mining experts, right? I mean, they said, okay, we need to find chains. Like, sure, then we're going to find chains. But then with Patrick, and we didn't want to find it. And we also looked back in these results, and as you will see later, also this method doesn't find any chains. We didn't really look into it at the time. We weren't critical enough. But then Patrick and I started to think, okay, so why doesn't it find chains? And if you now start to think about it, if your graph is sufficiently sparse, there's chains everywhere. Everything is a chain. And explaining stuff as a chain only makes sense if it stands out. So if you have a very dense graph, but there is a group of nodes that are just only a chain, yes, then it makes sense. But if you have a sparse graph, everything looks like a chain, and then it actually costs more by pointing out that things are a chain, because it could be this chain, could be that chain, who knows? Chains effectively don't exist in real-world graphs. But we didn't know this back then. So this is beautiful, but also completely useless. Maybe in molecules, I don't know, in molecules I don't think there's chains either, but I mean polymer chains, sure. Okay, good. So we use these scores or these intuitions that you've seen to score these things, and then, well, we assign the one with the lowest cost. Now we get into the painful part of this exercise, at least for me, because now we finally had a score, we had an intuition of what we wanted to do, right? We need to build an algorithm. Well, I was talking to my collaborators, and in the end, like I said, this is one of my most cited papers, and I mean, it got a lot of let's say follow-up work. So they were right, I was wrong, but I'm still a bit it still hurts the algorithms we present. So what would be the first, and there was really truly most stupid, let me underline that, right? Algorithm for finding a summary of the graph B after we've decomposed it and we gave it names. Trust me, your answer is either going to be spot on or not stupid enough. Any idea? Just toss it up. Way too advanced. More stupid, please. I think the animation is fucked, but so all of them. That is the plain algorithm. My heart bleeds. Okay, can we call this a summary? I mean, no, but okay, right? That's Can we do something slightly smarter, but still not that smart? We can think of, for each of these subgraphs, how many bits did we gain by encoding it as the structure we say it is, right? We found to be best, versus if we just leave it as error, right? That allows us to determine how many bits we save per structure. And then we can have a top K algorithm. You tell me how many structures, and that becomes that. So I order them up, and now there you go. And that is my summary. My heart still bleeds. Because how do I define K? And come on, right? If we add a little bit of MDL magic by also having a penalty for how complicated is the model, which means how many subgraphs are there, of which type are they, and then, well, encoding them specifically, because plain and top K ignore that what structures we even have, right? I mean, that's, so we went through all this effort to build this score, and so up, yeah, sure. And then we came up with greedy and forget. This is, I think, what you had in mind. What we do is we start with an empty model. We take our score, our subgraphs, we order them. We take the one where we save the most bits at the top. We put it into our summary, which is still underlined. Okay, this is so annoying. We see here that by keeping it, this one should be overlaying here, obviously. I have no idea why not. On my desktop it worked. We need fewer bits, that is good. We add the next best one. Oh, we costs bits, so let's not do this. We forget about it and we just greedily select. Oops, there we are. Okay, I was like, okay, this is a good baseline, right? I mean, this is a reasonable. I asked for a stupid method, right? I mean, that's yeah, this is the simplest you would do. And I said, okay, let's now find a real algorithm, right? One that can do this on the fly. And they're like, no. We don't do that here. I mean, we have now a method that works. Why should we make the paper more complicated? I think they were right, but I still don't like it. I think they were right in the sense that the method we presented was identified a good problem and a solution that was just good enough that people like, yeah, it works, but stupid enough that people like, I can do better. So it attracted a lot of research attention. But I still find it a bit of an insult to our own intelligence because we could have done better. But maybe this is the learning of this project for me, that I should embrace the stupid solutions more than I tend to do. Good. We will see the slightly more advanced version perhaps in a few minutes, otherwise next week. Good. Does it work? This is the number of bits for the Enron dataset. This is a big energy provider in the US. There was a huge scandal. And in the court cases of the scandal, all email traffic within the company was released, which made it a treasure trove for what the hell was going on there. So also a good target to be analyzed. Actually, you can see that by just plain, we already get some compression. And it explains almost all edges. Yeah, that's not a surprise, because if we have a ton of structures, then by taking the top 10 or the top 100, we explain much fewer edges, but already get some compression. And you remember from earlier lectures, some compression is already good enough, right? No compression is bad. That's the only thing that's bad. Greedy and forget, get 75% compression, explains, there with 40% of the edges. Decent, but main argument here, real graphs have structure. Our primitives can explain real structure in these graphs. Does it mean that we have all the structure? No, right? Adding more primitives, good idea, but at least we can already find something. And what is also good, where is this? Yeah, for example, here, you see that I didn't even list the chains because they were simply none found whatsoever, just zero. By which we have also a reality check that if we include now stupid terms in our vocabulary, the score prevents you from using them. That is good, right? So basically we have a protection against false discoveries, not, let's say, well, false negatives. Yeah, main structure types. Okay, good. So let me just walk through this. The top 3 stars in this data set were Kay Lay and Kenneth Lay, who happened to be the CEO at the time of the whole debacle, and then his replacement, Jeff Skilling. So those are the top, let's say, stars. So if you didn't know, fine, but finding stars in data, that's this one is more interesting. These were the top non-bipartite core. So this, what we were talking about earlier. And actually it's the top 2. And there is there was some affair between some colleagues going on, which then, well, became a public fight in a way, where a small group of people were broadcasting to many people who were not interacting at all, right? But they were sort of constantly discussing amongst each others. And there was also a discussion about the skiing excursion, where also most people just went along with it or didn't even respond. And there's a small core of people who did discuss and did all the organization. Okay, that is useful to extract from a graph, right? Not something that you can get trivially. Now, runtime, as we've said, I mean that it should be linear. Vogue is, well, near linear. So the exponent is 1.05, which, given what we are doing, I think is pretty good, right? I mean, that's, and reviewers also agree that 1.05 is still sufficiently linear to be allowed to the party. Good. Now, vocabulary were these 5 terms. What we could do is jellyfishes, so basically stars of stars. And also, actually, no, this is a jellyfish. What is this again? Well, if we let each of these be connected, then effectively you have for example, a network of mobile phone providers. So each mobile phone provider has their own customers, right? Most people don't have a subscription with multiple mobile phone providers, but the providers, they do talk to each other, otherwise you can't call each other, right? So if you look at calling networks, you find structures like this. So this would be potential candidates to expand the vocabulary on. Good. Okay. I'm going to use the next 10 minutes, if I may, with a slightly different slide deck. So let me stop this for a second. Yeah, I know. Then we fast forward to 2021. Let me actually do this like this. Duplicate. And share. Yep. I guess this one. Share. Yep. Okay. Oops. Yeah, go away. Yeah. Good. So March 10th, 2021. Took a few years, I think 7, but finally we picked up with some fresh set of hands and some fresh ideas on this idea. How can we now measure the similarity between 2 graphs, or actually describe the similarity? Because the idea we posited before was still purely measuring, compressed together versus, but actually now that we have Vogue, right? Suppose that we would have Super Vogue that could compress 2 graphs, which we don't have yet, right? We will see it in a second. It's called Momo. But then what we can actually do, we can also name what is similar and what is not. These 2 graphs, they both have big cliques connected like such and so. But this graph has something different than that graph. That's not just measuring, that is describing. And that is actually, I would say, a much more interesting question. Because how often do you really want to just measure how similar things are? Or actually, you want to know what makes them similar? And that's what I like about this approach very much. So why this? So here we have graphs. I mean, this was some protein-protein interaction, if I'm not mistaken, but it could also be molecules or whatnot. And sure, how similar are they? There's graph kernel similarity measures and whatnot. We can look at the connectivity structures and so on and so forth. But for similarity search, this is meaningful. Yeah, you want to find a molecule that looks as close as possible to this example. Sure, right? But if you have a larger graph, let's say protein interaction networks between this organism and that organism, then it's actually the question that you really want, okay, what makes them similar? And these proteins may have different names because they're not exactly genetically the same, right? I mean, and so on and so forth. Can we do something? We can also look into graph similarity over time. For example, these are topics in economy where in the late 90s, economics and neuroscience were completely separate because, well, economists believed that people are rational beings, right? Neuroscientists knew that no, right, we're all neurotic as hell. But the merger of the two fields, or at least the connectivity fields, that really became a thing in the early and later 2000s and up to 2010. And you see now a lot of work that actually take into account, okay, how do human brains process information and how do they lead to decisions? And well, that arrives at better or at least more accurate economic models. So effectively what we have a citation network or a topic network in the past and the future, which are two graphs. They encode information about the same subjects, but not necessarily a matching between the same nodes. Doesn't even exist, right? Because papers written in 1997, yeah, 2010, what are we talking about? It may not be the same people, right? But you have a phenomenon measured in two graphs. You would like to know how do they relate. We do these comparisons all the time. Like, from a related domain, the same point in time, for example, the protein-protein that I just said. Same domain, different points in time, like in the economics example, but sometimes it's also completely loosely, right? But, let's say a protein interaction network from an extinct mammal or dinosaur versus something like that. Where it's just like, let's say the patterns of food intake have changed because environmental situation has changed, right? Stuff like this. Yeah, or let's say also a good example, COVID versus Spanish flu. Why do we care about measuring similarities, determining similarities of graphs? Typically, understanding. And this is one of those points where everything is obvious once you see it, right? But asking this stupid little question, why do we do this? Many people don't do, or definitely don't do often enough. And I would posit that the hundreds of papers on graph similarity metrics that are out there, most of them are completely useless. And it's more an answer to the question, how do we do a certain thing without asking, like, why do we do it or what should it be doing? So what's the problem? Current methods work on graph similarity measurement. So the question they ask is, how similar are these graphs? Which again is a very natural question, but it is not the right question. It is, how are these graphs similar? And if in addition we can give a number for how similar they are, great, but how are they similar? It's really just changing the stress in the sentence that all of a sudden, well, gives you some enlightenment and gives at least the idea for also a completely different class of methods. And also points out why existing methods, well, don't answer this. Here, for example, if I color the nodes that form a star structure yellow, I color the ones that form a click blue. Let's see, the bipartite graph is red, and I think the bipartite core is then pink, if I'm not mistaken. These two graphs are over completely different types of nodes, but they share some structure. Previously, you might have seen it already, right? But if you would just been calculating average degree or clustering coefficient or whatnot, right? Vogue would have given you something left, something right, but no. But here we can say that, hey, there is a star structure. Oh, oops. Okay. No. Okay, wait. I'm in PDF, so I don't have my pointer. Okay, well, then I could just do this. So what we have is that between these two graphs, what we can think about it, there is a common model, a confounding model, if you wish, that consists of a star, of a clique, and I think this is then a bipartite core. And on the left-hand side, well, what we have is that each of those have more nodes, right? So they're relatively large. So I drew this a bit larger. And in addition, we have this bipartite graph. Where on the right-hand side, well, they're relatively sparse, and we don't have this bipartite graph. But finding this common model is now the goal, and how they connect. So how can we do this? The general idea, just instantiating what we were discussing already here, we need effectively models of models. We need to have a common model that we use to describe both graphs. And we could do this in theory by literally putting the two graphs somehow together into one graph, but then you need to do graph matching between them. I don't know how to do this. So we thought, okay, why don't we keep the two graphs separately, have a model per graph, and think of a meta model that allows us to succinctly describe the models, the optimal models for the individual graphs. And the more similar these two models are, the easier it will be to describe these models given the meta model. Because if they're the same, then the meta model is just going to be, well, one of those, and then it's just copy, copy. And we are exactly at this idea that we discussed earlier, that if the two graphs are exactly the same, you just need one program, right? So effectively what we have is that we have a model M12, so model for graph 1 and graph 2. Then we have some delta that takes this model in and transforms it into the model for graph 1 that we found to be optimal. Vogue and also Momo and in its internal algorithm are not optimal per se, but we pretend that they're optimal because we don't have anything better. And how do we find this model? By minimizing effectively this MDL term here. You can imagine the L's around it. So graph 1 is described as a model 1, plus then, well, the parts of graph 1 that we can't describe, it's just a model, right? And we do the same thing for graph 2. So this is the overall thing that we want to minimize. So we start by running Beppo. So I hope that some of you recognize the characters' names, right? I mean, that's so the stories of Momo, which is one of the favorite books by the main author, Corina. So we first summarize using, let's say, the grandchild of Vogue called Beppo. Then from that, we have an algorithm that finds this merged model called Gigi. And then, well, we can also, once we have that, measure the similarity in terms of bits. This is this normalized model distance where, well, look, actually, I don't have to go through it. I mean, it's the same idea we just had. It doesn't really matter. How does Beppo work? We decompose the graph into overlapping structures. We can use, again, slash and burn for this, right? Can you use something else? We don't want to reinvent every wheel. We now looked at 4 specific structures. We dropped the chains because they don't really make sense for us. We have cliques, we have stars, bicliques, or star cliques, that's what we call them. I thought bipartite cores, but well, anyway, star cliques. So these are all stars, and they link then to a clique. So these are the diamonds. Can we extend the vocabulary here? Yes, but these are the ones that we liked, and I mean that's so it's homework for the interested reader to expand on this if you wish. And how the method then works, very similar to Vogue. How it scores things is a bit more advanced. We're using maximum entropy model to basically get a maximum likelihood estimate and blah, blah, blah. The general idea is the same. Find those groups of nodes, give them a name, find the best compressing set of names. Now I have 2 models. Now we want to align them. How do we do this? So structure sets or models S1 and S2. Now, in some cases, we know exactly the alignment between the nodes in the left-hand graph and the right-hand graph. Because it might be, let's say, a social network over time, let's say today versus a year ago. And if we now, let's focus on that, we didn't allow anybody new into the network, right, just to avoid that discussion. But we can see, okay, what happened, right? I mean, so did things just grow? I mean, it's just become more, is it the same? Or did this clique of friends sort of disband and nobody likes each other anymore and now there's this clique, something like that, right? But if we know that this node corresponds here to that node there, well, it would be stupid to throw away this information, right? In most cases, you don't have a full alignment. Some cases you have only a partial alignment. Let's say we have social network over time, but hey, there's new users, which I can't really match, right? I mean, that's there's like in protein-protein interaction networks, we might know that this one has the same role as that one between this and that organism. But what those do, God knows, right? So we can't link them. And sometimes we really have no clue. There's no alignment between the two graphs. So what we wanted is an algorithm that can handle each of those three cases. Most methods out there can only handle the full alignment case, or if they want to sort of like, well, link two graphs. I mean, and if you have a fully aligned graph or two fully aligned graphs, you can also just overlay them and you have one graph. So it's kind of cheating. Now, the idea that we have is that if I now found in the left graph a clique and in the right graph a clique, and I know that, let's say, some or all of the nodes in these cliques are linked between them, I know that this clique is effectively that clique, right? Similarly, if I know that nodes here are connected to nodes there, but here I call it a clique and here it's now a star, and it was really not the right thing to call this a clique, then, well, somehow this clique's morphed into a star or vice versa, right? But if we don't have any of such alignment information, then the best thing we can do is think of like, okay, if we have a, let's say, a very dense clique, right? Let's say 99% density, right? So 99% of the edges within this clique are here, right? And in this graph, I have let's say an 85% dense clique. It might be the best guess to sort of, okay, this clique corresponds to that clique, but I'm not 100% certain. The idea is there that we model this with this meta model as a clique of roughly, let's say, the average density, and in both directions we have to encode the delta. Like, okay, there's a dense clique of, let's say, for 90%, and here we have a delta cost of plus 9%, and here minus so much percent. That is the general idea. So, effectively, we greedily match structures by the average Jakar similarity on the alignment, the node alignment, if we have it, and otherwise, well, we just relook at the structures themselves. I'm going to skip over this. Does this work? So, and I'm skipping over the algorithm as such entirely, right? But that was also not the point of this part of the lecture. We looked at a wide array of different graphs. We looked at abstract data, we looked at network data, we looked at protein interaction data, we looked at law data. So law in Germany, law in the US, at, let's say, the federal level. I mean, how are those connected and how do they develop over time? Like the widest array of domains you can think of. As you can see, they also together cover a large part of, well, cases in the sense of like how large are these graphs, how dense are they, how many nodes, how many edges, and so on and so forth. And each of those are collections of graphs, not an individual graph, right? Because we want to do these similarities. Is the method, well, does it finish? Yes. So it's again this linear-ish type of algorithm. And what we see, whether this is interesting or not, I don't know in this particular case, but it's something that I just want to highlight. We now broke down the runtimes for each of these classes of graphs. So each dot is a graph, or actually a pair of graphs to be precise, from a collection. And as you can see, the green ones, they take more computation, even though they're actually smaller than the red ones. So just to point out that typically in any paper, if people report runtimes at all, it's an average. But averages are very, well, yeah, very limited in the information they provide, right? It's a bit like with medicine in general and personalized medicine, right? I mean, that's this pill has an 80% chance of curing disease X, and suppose that you have the symptoms of disease X, are you going to be the 80% or the 20%? That's kind of useful information, right? And if it now turns out that it's more effective for women than for men or vice versa, this is very useful information. Same thing here, right? So always stay critical there too. This is the top star that Beppo finds in citation network data. I'm here. So I also, yeah, this is the paper with Yu Kang. And let me see. So who else? Wait a second, where is... Oh, they're not part of this graph. This is an overlapping one. So I was looking for Leman, and I was looking for Hang Hang, and a number of others that I also collaborated with, former students of Christos. But what Beppo can do is it doesn't just overlap on nodes, but also on edges. So this means that you have a much more fine-grained view on the data, where it's not just you being part of, well, let's say being a pivot point of multiple cliques. No, there can actually be a sub part of this clique is, let's say, also part of the football club, and a part of this club is also part of the whatever. I mean, that's you met at high school, so you really allow overlaps here. This is why I couldn't find my co-authors. Okay. The models that we have, we can draw them. And so basically, these structures can be connected. In this data, these were sort of protein interaction networks in different organs. They are essentially all connected. I mean, just by looking at these plots, you can already see that these tissues, some tissues are more similar than others. Right? Method didn't know that. Method just finds cliques and, well, stars, or yeah, these are cliques and stars. And then by the sizes, you just see that, well, these are definitely more similar than, well, this part of the tissue set. That's already interesting by itself. Now, next, because here, I mean, you have what was read. Okay, this was this star clique, right? So here we have in the appendix and the cecum, we have these star cliques that in these tissues we absolutely don't have. This is already then a hint towards how similar are these, and what is now the best match between these models. For that, we need to look into GG. What does GG do? So for the esophagus and the colon, so these are, what is it? Colon and esophagus. So they're quite dissimilar in this regard. And what you see is that here you have the star clique, right, which the other one definitely doesn't have. A number of cliques and a number of bipartites. The colon has a lot more stars that the esophagus doesn't have, but there is definitely a core that makes them quite similar. So what this shows us is sort of like two sides that are they super similar? No, but they share a core similarity, which just by looking at these individual models, you would not see. You really need to sort of look at them together. And by figuring out what is now the best joint compression, that's what you get. Yeah, so you can do this over all sorts of pairs, and well, this makes biological sense. The measurement of how similar are these graphs that we discussed, so by just the compression, we can also instantiate this, then we get these values. I don't know how to validate these. But basically what it says is that this is computer science, and this is, I think, law. These are abstracts, I think, if I'm not mistaken. Those are very similar. The others less similar between pairs. Well, yeah, that might make sense because abstracts typically have the same structure, but otherwise, this is more of a slide. We can compute this. If you're interested in similarities, here you are. Okay, this takes too much time to explain. So what's next? This was in 2021. This line of research, well, we deviated a little bit, so we're not so much further than what we have here. We would like to expand to weighted graphs, to attributed graphs. And do you see the pattern from what I said at the beginning? But everybody starts with, and then you're stuck. And so when we started this project, Corinne said, okay, whatever we do, I do not want to get stuck at undirected, unlabeled, and so on graphs. So I don't know. Then we just start with it's fine. And in the end, we have a method that just exactly that's right. Already much more than other methods can do. I mean, that I have to say. But building this up to include weighted graphs, in this particular case, it's not fully trivial because you need a scoring model that doesn't, so basically the MDL score, how do we factor in weights? I don't know yet. But also in just measuring similarities between then structures, how do we incorporate this? So we would need to rethink this. Directions, I think, is reasonably easy to plug in, maybe. Attributes, again, big open question. Now, thinking of, for example, molecules and large molecules, you would really need that. This is not really the answer for that particular domain. So are we done yet? No. Discovering the vocabulary dynamically. We discussed this at length, right? And well, just to point out, I'm definitely not against it, but it is certainly an open question. The methods that you've seen today had the advantage that we know what we're looking at. If the method gives you something, it says this is a click, then you know what is a click. And if it's an arbitrary connectivity structure that you really don't know what it is, then what defines it? And either this is because it has meaning or because you can point it out often in one graph or often over many other graphs. But you will need this notion of frequency over something in order for something to be explicable, I believe. I'm happy to be challenged there. Yeah, and how would you incorporate domain-specific background knowledge beyond that this node corresponds to that one? Like, of course, these are not connected to those because such and such and so. How would you incorporate this? I don't know. And then so this is where we're doing models of models or the meta model, but what structures of structures, a clique of cliques. This goes a bit in the direction of what Timmer proposed, right? Or a star of cliques. And how can we give names to that? And I think this direction is quite promising. As long as we think about it, well, not from the simplest way of like just mine things, connect them, and just keep on iterating, right? I mean, then you get this hierarchical summary. But by having a bit more fine-grained connectivity, I think you can get a lot more insight into what certain domains, what is happening. Good. That brings me to the end. Thank you for your attention. It's 2 minutes to 12. I talked for long enough, so class dismissed. See you next week. Next week, final lecture. So this is going to be the wrap-up. Plus, I will present. I'll give you a choice of 1, 2, or 3 topics, and I will then, well, whichever gets the most votes by you, I will then lecture about. Good. So till then, bye-bye.